Hello everybody, welcome to this tutorial. This tutorial is somehow the continuum of the last tutorial, which was about creating iOS and Android application using Simulink and Matlab, using Simulink support packages for Android devices. In the last tutorial, I just demonstrated to you so how can you set up your phone to make it ready for building application from Simulink and deploying the application from Simulink to the Android device. So if you haven't watched the last video and you haven't done this process and it's your first time, so please pause this video, go back to the last tutorial so you know how to set up your phone prior to this tutorial, because I'm not going to go through those tutorials. There are very simple steps you have to follow to set up your phone. In this tutorial, I'm going to use the raw sensors inside our phone. Most of the smartphones right now have all the sensors you need: gyroscope, magnetometer, accelerometers. So we are going to use it to create our own AHRS. For those of you that you don't know what is AHRS, it is Attitude and Horizon Reference System. Okay, I'm going to talk about this a little in the introduction, and then we're going to start our business. Okay, so what is AHRS? For aerospace engineers, mechanical engineers, control engineers, and pilots, attitude is a well-known word. For example, in the middle screen, you can see this is an attitude indicator of an aircraft. It shows that this aircraft is at 30 degrees banks to the right, means the roll is 30 degrees to the right, or better to say, in an engineering speaking, minus 30 degrees roll and 20 degrees of pitch. So this shows the pilot that what attitude is its aircraft relative to inertial frame, or better to say, for simplification, relative to Earth. The person that is looking you from outside see your aircraft is in right turn, right bank, and nose up position. For control analysis, stability augmentation, or any other analysis on your aircraft or vehicle, you need to know the attitude, you need to know the orientation. So this is where you find that you need AHRS. AHRS are categorized in different forms in market based on price, based on application. You can find very low price AHRS, and of course there are some AHRS in the market that worth more than $10,000 or even more. So AHRS are being used in maybe a toy quadcopter, a toy car, or even in a ballistic missile or even air-to-air missile. All of them have AHRS, but the precision is different, the operation range and everything is different, but the concept behind that is the same. So right now we know what is AHRS. But you might have heard about IMU. So what's the difference between IMU and AHRS? IMU is inertial measurement units and AHRS is attitude horizon reference system. I'm going to talk in a very simplified form. IMU is the sensors you have, and mostly it consists of gyroscope, accelerometer, and magnetometer. These are the raw output of your sensors. So right now that you're watching this video, if you're watching this video in your smartphone, you already have an IMU in your hand, because your phone might have accelerometer, gyroscope, and magnetometer. But what is the difference between AHRS? AHRS is the attitude indicator. It means it shows you, for example, roll, pitch, and yaw. In this picture, you can see what's happening. We have accelerometer, gyroscope, and magnetometer that are outputs of our IMU, is the raw output of these sensors. For example, you have AX, AY, AZ, GX, GY, GZ, and MX, MY, and MZ. And then you're going to use some filters, some estimators filters, such as complementary filters, Kalman filters, EKF or extended Kalman filter, and so on. Using these filters, you are going to estimate the roll, pitch, and yaw. This is the part we're going to use in this tutorial. We're going to use the output of our sensor to estimate our orientation, estimate the orientation of our smartphone. And by the way, if you know, if you have just think a little, you know that you can find the orientation of your smartphone with only accelerometer if your vehicle is stationary and it's not moving and it's not accelerating. I'm going to show you what it means in the next parts of this video. But if you're going to estimate the attitude of a vehicle that's accelerating, such as an aircraft or such as an quadcopter, you can't just rely on accelerometer. You need gyroscope as well. We're going to talk about it more in the continuing of this tutorial. One of the most common ways for estimating the attitude based on sensors outputs is using Kalman filters. Another methods are available such as complementary filter and so on, but Kalman filter is maybe one of the optimum for our purpose. Better ways are available such as extended Kalman filter, but we are going to use the first order linear Kalman filter here. So what is Kalman filter? I'm not going to go through the mathematics and the concepts. I'm not master on mathematics. I'm just telling you the meanings and concept behind the Kalman filter. Kalman filter is being used for estimating the states of a system, for removing some noise and this kind of stuff. In the right picture, you see that in right and left pictures, you see that there is a prediction. So before anything happens, before a time index t0, we have a prediction of our system states in a t plus 1. Based on our, for example, you are driving your car. You know how much throttle you're applying, you know the steering position, and so you have a prediction that 1 second or 2 seconds later, where is your car? And then you have some methods for measuring that. By the time passes, you can measure that, and then you comparing the prediction and measurements, you find an optimal state estimator, which is x hat k. Through the time that everything is happening when you're driving, using comparing the prediction and measurements, you come to the best and optimum state estimation that you can see in the same picture. And the mathematical formulation is available in the bottom pictures. There are some variables such as process covariance matrix, sensor noise covariance, predicted state noise matrix, and so on. I'm not going to go through this, but if you know what you are doing, you can change the parameters and covariance matrix inside our model. So if you don't know anything about it, no big choice, no big problem, you can continue. But for an advanced applications, you need to know what you're doing. You need to know about these variables and scenario. Okay, so we know right now we know what is AHRS, we know what is Kalman filter, we know the difference between IMU and AHRS, and we know what we are going to do. So everything is ready. What you're going to need for this tutorial is having a Matlab and Simulink. You can use for Android development, you can use Matlab 2014b and later. But because in this model I'm going to use some gauges and panels, you have to have Matlab 2019b and later. If you don't want to use the gauges, maybe you can still use this file. I don't know, but if you have a problem, you can ask me and I will give you the older version compatible of the files. So you need everything, but you need the main things that you need is the IMU. You can use an external IMU. Maybe you are developing an autopilot for an aircraft, so your source is your IMU on board the aircraft. But right now, IMU is in your hand. You're going to use your phone. Most of the advanced phones have all the sensors you need, and they are actually very good for the normal purposes. You can't use this sensor fusion for rocket science or for guidance and stabilizing a rocket, but you can use it for maybe toys, maybe small quadcopters, for rovers, and for some developments and scientific analysis and for studying and teaching to students. It's a very good tool. So okay, you can see that we have selected our phone as IMU, and now we're going to implement our model and simulation and files in Simulink, and then we deploy it to the Android device. And by the way, you can do this tutorial on iOS devices as well. You just need to change the sensor inputs from Android to iOS. But as I told you in the last tutorial, I don't have access to Apple Developer ID, so I can't do that right now. So it's based on you, but it shouldn't be hard, just changing the blocks. Before starting, let me show you how you can access the raw data of your sensor. Just go and install this application. It's called Sensors with the red signs. You can access the real-time data of the sensors of your IMU. For example, you can access to the part number, the resolution, and different kind of sensor. You have accelerometer, gyro, magnetometer, location, or anything. For example, the proximity, or this one is the barometers, and so on. You can access and see which sensors your mobile phone is equipped. Okay, let's start. This is the GitHub page that the link is available in the description. Just go to the GitHub. It may be different from the time that you're seeing this because I'm going to update to different, upgrade it to different versions as well. So it should be just similar to this. Download the file, or you can directly download it from the Matlab add-on page and import it in your Matlab. When you open the Simulink file, you will face with this version. Because I'm using some gauges here, you need to have Matlab 2019B and latest, but I already uploaded a legacy version as well. Before that, you make sure you have installed Simulink support package for Android device or for iOS device if you want to change this for iOS. And this is the library that I have been using for the Kalman filter and theoretical calculations. I used this person's file for my calculation. IMU sensor fusion with linear Kalman filter by Roger van Ransberg. Okay, this is the Simulink support package for Android. This time we're going to use sensors. You can see we have accelerometer and different kind of sensors here. We're going to use accelerometer, magnetometer, and gyroscope. And as you can see, there is also an orientation here. So why don't we use this orientation instead of doing all this process to get the attitude? This is the reason why. You can see there is a very good tutorial about sensor fusion and understanding sensor fusion and why this is so challenging to get the attitude in flight and in the motion. I recommend you go ahead and watch this tutorial series. I will put the link in the description. In this tutorial you will understand why it is challenging to have and why we need sensor fusion. But for a quick demonstration, you can see this is the reason why it's so hard. Because as you can see, if you want to get the orientation from accelerometer only, you are only relying on gravity vectors. When everything is stationary, there is no problem because the gravity always faces down and we know the gravity. But the problem is accelerometer doesn't measure gravity. It measures all the accelerations on the sensor. So if we are accelerating in x-axis, the gravity vector will be tilted backwards, so you don't have access to the accelerometer gravity. You will know the total accelerometer. That's why we need gyroscope to fuse it together with accelerometer to correct this error. Okay, let's start. There is a gain here. You won't need this because I've already calibrated it. It's because if you want to just manipulate the effect of gyro just for demonstration, you won't need this. It will always be on 1. You can just change the value in the application to make sure that the effect of gyro is available there, and there is nothing wrong. Okay, let's start from the top. Each one of this block is associated with one of the angle. But before starting, let me show you the axis of this sensor, so how the sensor is located inside our mobile and what should we do to make sure which face of the mobile is what and which angle is what. This is the sensor documentation of the Simulink support package for Android. As you can see here, the x-axis is toward the right side and the y-axis toward the left. Or if you see the mobile in horizontal plane, you see X is forward and Y is left. But usually in an airplane or aircraft, we will face the X-axis on forward and Y at the right and Z to the bottom, to the Earth center. So I'm going to rotate 2 times. We have 2 rotation. I'm going to reverse the Y and reverse the Z. As you can see, these are the minus ones here from the sensor. Or you can just multiply to a rotation matrix if you know what you're doing. I just put it simple and put the minus signs for the Y and Z axis. Then for the filter, Kalman filter, as I told you, we need an initial prediction. So we use the measurement of the orientation by accelerometer as an initial approximation, initial guess. Very simple formulation. We use trigonometric equations to get the orientation by accelerometer. This is an orientation that only works when the vehicle is stationary, and we are going to use it for the initial prediction, and then we are going to feed it through the Kalman filter. For the Kalman filter, we're going to need the gyro. Which gyro? The first block is for the roll angle, and for roll angle, you know that we need G around the gyro around the x-axis. And the other ones that you can see, such as R, covariance of covariance bias, X, and other stuff for the theoretical is about the Kalman filters. I'm not going to go through that, and I'm not a mathematical expert. I'm just using the code that I found from the internet. And the T of S is the sample time. I have set the sample times for the code in the settings. To change the sample times, go to the Model Explorer and select the projects that you're working on, which is Kalman Android AHRS. Go to Properties, and in callbacks and init function, you can change the T of S. Right now it is 100 Hertz. It means 1.01 seconds. And the output, as you can see, we need right now we need 2 of them. First one is roll rate and the other one is roll angle, and the most important one is the roll angle. You see, I have combined the signals from the filtered roll angle that comes out of Kalman filter and the one from initial guess, which is only using accelerometer, and I plot both of them together with a scope. Exactly the same thing goes with the pitch angle. The difference is that we are going to use gyro around y-axis, and for z-axis it's a little different because we cannot have initial guess for the heading or yaw based on accelerometer. So initial guess is based on magnetometer, and then we combine it with g of z, so gyro around the z-axis. Again, everything is the same here. As you can see, the initial guess is being calculated by this function. It's just trigonometric equations that gets the heading based on the magnetic field of the Earth and corrected by the roll and pitch of the vehicle. And then it's going to be feed forward to the magnetic heading, and then it's going to go forward to our Kalman filter. Everything is the same. But don't use these things for the real project. These are just for demonstration. Definitely you need different covariance, different parameter for each of the sensors. And there is a built-in AHRS function in the Matlab that I couldn't make it work. I don't know what's the problem. I did a lot to make it work, but nothing happened. So I just put it in the comment in the code. So if any of you liked it or could do anything with that, please let me know, because I couldn't get the result by the built-in function for the AHRS in Simulink. That's almost everything in this code. I don't think there's anything else left here. But right now I'm going to show you how we can deploy it to our Android. Right now, just connect your Android phone to this computer. You will hear the beep sign. Remember, in the last video I told you how to enable the development mode for your Android OS and the configuration you need for deploying code to Android. After everything is done, just if you can use the monitor and tune to have the Windows, Simulink and Android in parallel working together, but in a slower speed. But you can build it and deploy it to have a standalone application on your phone. But before building, make sure the configuration is okay, the Android device is selected. If you faced with any error that something just haven't been loaded, come to this screen and put the hardware setting on none, click apply, and again come back and put it on Android device. And in code generation, I usually put it on faster runs. But code generation doesn't matter right now because we are just going to deploy the code directly to the application and we are not going to use it. And this error because the active directory is not the one that I have saved my Simulink model. Just go change your working directory to the folder that your Simulink file is located. Come back to Simulink and click build and deploy. It might take a long time if your computer is not fast enough. Maybe even to 5 or 10 minutes if your computer is slow. After the building finish, you will see a new application appears on your screen and it is ready and it will be open. You will face with this screen that you have there are 3 gauges, roll, pitch and heading, each one associated with the angles you want. You can sweep the screen to get the scopes. For example, as you can see, I am changing the rolls and pitch and headings. This is not exactly what I want or what I can work on a project, but it's a good start. For example, this one is the pitch angle. You will see the yellow line is our initial guess based on the accelerometer. It gets noisy when I change when I do some back and forth motion, putting some G's and acceleration to my sensors, my phone. But the blue one, which is the filtered version, is doing great. It follows when the orientation is changing, but it is not following the noise. When I change, adding some unwanted G's and vibrations and acceleration, you can see the yellow line get distracted, but the blue one doesn't. And this one is for heading. As you can see, it's almost toward the north right now, and when I rotate it clockwise, the angle increased and it's almost the east right now. Everything is working here, but it's just a start. I'm not satisfied with that yet for a real project. So if any of you have a better solution, just please give me. And by the way, this slider is, as I told you, is for the effect of the gyro. You can put it on 0 and you will see that it takes a long time. The blue line follows because it's not working gyro anymore. It shows that the gyro is stationary. And if you put it all the way to the up, you will see that the gyro will overshoot because the gyro number is exaggerated. You will see it overshoots the orientation with accelerometer. It's not going to do anything for you. It's just for the seeing that the gyro is working and the code is working. Okay, and I was telling you this is the code generation report. You can go and see what's exactly happening, but these are not the codes that you need. If you want the source codes that you can work with Gradle or Android Studio, you should access to the Java codes that is created automatically. Just go to your working directory, and after the build, you can see on the folder. You will see the Gradle source files, and you can see the Gradle design files, and you can access to the source under your repository name. These are the source file of the code that is auto-generated by Matlab. This is everything that I put here for you in this tutorial. I think I've covered everything, but remember, this is the first version. This is under development and everything is not the way it should. I'm working on it to make it better, so use it at your own risk if you're working on a project. And this is only for demonstration and testing and evaluations. Okay, this is where I want to pause this video. I think it's enough. And right now you know everything about AHRS with Kalman filter. And if you have followed the video, you have deployed this model to your Android device and it's ready to use. You can extend this feature to some other application. You can use it as a teaching tools to your students or exercises of your homeworks. You're using some filters, adding noise reduction filter to the output, use it in your car to estimate the orientation or of your car or bicycle. So you can do everything you want. You can add some filters, low pass filters, moving average, and different kind of filters for better make the results better. Okay, I think that's enough. If you have any question, please leave it in the comments, and if you have some feedbacks and questions, please let me know. And if you want to if you don't want to miss the next episodes of this tutorials, please like and subscribe this channel. I'm going to continue this kind of topics so you as an engineer can do everything you want inside your phone, smartphone. Maybe in the next tutorial I talk about communicating with Bluetooth and serial devices. Thank you for watching. Happy coding and happy flying.